Something is pulling particles out of nothing, not magic, not metaphor. Real particles, electrons, photons, pairs of matter and antimatter, blinking into existence where nothing existed a fraction of a second before. Physicists have measured it. Engineers have built devices that depend on it. And every single atom in your body exists because of a process that started the same way. Empty space, it turns out, is not empty at all. It seethes, it churns. It borrows energy from the future and pays it back so fast that the universe never notices. How does that work? Why does it happen? And what does it mean that the vacuum of space is one of the most violent, restless, particle-producing environments in the known universe? Stay with this, because what you're about to hear will change the way you see the word nothing forever. Let's get the stage set first. For most of human history, people assumed that empty space was simply that, empty, a void, a nothing. Ancient Greek thinkers debated whether a true vacuum could even exist. The ones who said it could not, like Aristotle, had enormous influence. Nature abhors a vacuum, he wrote, and for almost 2,000 years that phrase carried real scientific weight. Then came the 17th century. Evangelista Torricelli, working in Florence in 1644, created the first laboratory vacuum using a glass tube and mercury. Above the mercury sat a sealed space with nothing in it, or so it appeared. The question of what was really in that space did not get a serious answer for almost 300 more years. If you are watching this channel and want more content that traces how fundamental physics actually developed, from the mercury tubes of Florence to the quantum labs of today, subscribe now. It is the best way to support the work we do here. Drop your city in the comments too. This script draws on sources including David Kaiser's work at the Massachusetts Institute of Technology on the history of quantum field theory, and the experimental records of Hendrik Casimir, the Dutch physicist, who in 1948 predicted a measurable force that could only exist if empty space was full of invisible activity. More on him shortly. Now back to the story. The modern answer to what fills a vacuum begins with quantum mechanics, which took shape in the 1920s. The core insight is simple to state and almost impossible to fully absorb. At very small scales, the universe does not allow things to be perfectly still. This is not a limitation of our instruments. It is a law of nature, built into the structure of reality. Werner Heisenberg stated it precisely in 1927. His uncertainty principle says that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. But here is the part that matters for empty space. There is a version of this principle that applies to energy and time as well. You cannot know both the exact energy of a system and the exact time of that measurement simultaneously. The product of the uncertainty in energy and the uncertainty in time must always be greater than a fixed number, a number called the reduced Planck constant, which is approximately 1.05 times 10 to the power of negative 34 joule seconds. What this means in practice is startling. For extremely short windows of time, fractions of a second so small they have no common name, the energy of a region of space can fluctuate wildly. The universe, in a sense, allows the books to be unbalanced for a moment as long as they balance again fast enough. These energy fluctuations are not metaphorical. They are not a way of saying we do not have enough information. They are real physical events that leave real physical marks. And the most dramatic mark they leave is the spontaneous creation of particle pairs. Here is how that works. Energy and matter are interchangeable. Albert Einstein showed this in 1905 with the most famous equation in science. Energy equals mass times the speed of light squared. That equation runs in both directions. Just as matter can release energy, energy can become matter. If a region of space temporarily possesses enough energy, even borrowed energy from a quantum fluctuation, that energy can materialize as a particle and its antimatter partner. A particle always comes with its antiparticle. An electron comes with a positron. A quark comes with an antiquark. These pairs appear together, exist together for an unimaginably short time, and then annihilate each other, returning their borrowed energy to the vacuum. The whole process happens so fast that no law of physics is violated. The debt is paid before the universe can audit the books. Physicists call these pairs virtual particles. The word virtual is important. It does not mean fake or imaginary. It means that these particles exist in a state that cannot be directly observed while they are in it, because to observe them would require more time than they exist. They are real enough to exert measurable forces. They are real enough that the entire architecture of modern physics, a framework called quantum field theory, depends on their existence. But they are not real in the way that the electrons in a copper wire are real. They live and die in the sub-threshold realm between existence and non-existence, popping in and out on timescales that range from 10 to the negative 21st second for the lightest particles to intervals so brief they approach the physical limits of time itself. How brief is brief? The rest mass energy of an electron is approximately 0.511 mega electron volts. Using Heisenberg's energy-time uncertainty relation, An electron-positron pair can exist as virtual particles for a maximum of approximately 1.3 times 10 to the negative 21st seconds before they must annihilate. That is 1.3 zeptoseconds. The fastest camera ever built, as of the early 21st century, could capture events occurring on timescales of tens of attoseconds, 10 to the negative 18 seconds. To observe a virtual electron-positron pair directly would require a device roughly 1,000 times faster than that. We cannot see them directly. We see only what they leave behind, and what they leave behind is enough. The field that governs all of this is called quantum electrodynamics, or QED for short. It was developed in the late 1940s by three physicists who would share the Nobel Prize in 1965: Richard Feynman, Julian Schwinger, and Netiro Tominaga. Working independently, all three arrived at the same mathematical framework for describing how light and matter interact through the exchange of virtual particles. Feynman's version used a visual tool he invented himself: diagrams that show particles as lines and their interactions as vertices where lines meet. In a Feynman diagram, the exchange of a virtual photon between two electrons, for example, looks like two lines with a wavy line connecting them. That wavy line is the virtual photon. It carries the electromagnetic force between them. It exists only in the transaction. Before going further, it helps to understand what a quantum field actually is, because the term does a lot of work in this story. A field, in physics, is a quantity that has a value at every point in space and time. Temperature is a field. Every point in a room has a temperature. The electromagnetic field has a value, a strength, and direction at every point in space. In quantum field theory, every fundamental particle is understood not as a tiny solid object, but as an excitation of an underlying field. The electron field fills all of space. When it is excited in a particular region, what you see is an electron. When it settles back down, the electron is gone. The photon is an excitation of the electromagnetic field. The quarks inside a proton are excitations of the quark fields. Every particle is a ripple in a field that is otherwise just sitting there at its ground state throughout the universe. And that ground state, as Heisenberg's principle demands, is never perfectly still. The ground state of every quantum field is active. It ripples, it fluctuates, it produces virtual excitations, virtual particles, constantly and everywhere. Quantum electrodynamics is the most precisely tested theory in the history of science. One of its predictions involves the magnetic moment of the electron, a measure of how strongly the electron responds to a magnetic field. The theoretical prediction of this value, worked out using quantum field theory and the constant appearance of virtual particle corrections, matches the experimental measurement to 11 decimal places. The agreement is equivalent to predicting the distance from New York City to Los Angeles, about 4,500 kilometers, to within the width of a human hair. No other scientific theory has been verified to this level of precision. The virtual particles are not a mathematical trick. They are load-bearing elements of the most accurate model of physical reality ever constructed. Now to the experiment that made all of this tangible. In 1948, Hendrik Casimir was a physicist at Philips Research Laboratories in Eindhoven, Netherlands. He had been thinking about the behavior of colloidal particles, tiny particles suspended in liquid, and their tendency to clump together. His colleague, Dirk Polder, helped him realize that the force causing this clumping was related to quantum fluctuations in the electromagnetic field. From there, Casimir made a bold prediction. Take two perfectly flat, uncharged, conducting metal plates. Place them very close together in a vacuum, so close that no light can fit between them except light of extremely short wavelength. What happens? According to classical physics, nothing. There is no charge between the plates. There is no magnetic field. There is no known force that should cause them to attract or repel. But according to quantum field theory, something specific should happen. The space between the plates, being so narrow, restricts which virtual photon wavelengths can exist in that gap. Only photons whose wavelength fits an exact integer number of times into the gap can form there. Outside the plates, all wavelengths of virtual photons exist in the vacuum, unrestricted. This means there is more vacuum energy pushing inward from outside the plates than there is pushing outward from between them. The result is a net inward force. The plates should be pushed together by nothing, by the pressure of empty space. Casimir predicted the magnitude of this force mathematically. For two plates each with an area of 1 square centimeter, separated by 1 micrometer, 1/1,000,000th of a meter, the force should be approximately 0.013 micronewtons. That is a tiny force. It is roughly the weight of a single human red blood cell acting across that surface. But it is a specific, calculable, non-zero force arising entirely from quantum fluctuations in the vacuum. The Casimir Effect, as it became known, was extremely difficult to measure for decades because it required plates that were almost perfectly flat and almost perfectly parallel, and the force was so small that vibrations and electrical contamination overwhelmed it. The first convincing experimental confirmation came in 1997 when physicist Steve Lamoureux at the University of Washington measured the force between a flat plate and a sphere using a torsion pendulum. His results agreed with Casimir's prediction to within 5%. More refined measurements followed. In 2001, a team at Bell Laboratories confirmed the force with even greater precision. The vacuum pushes, the plates move, the math works. The Casimir effect has an interesting dependence on geometry. When the two conducting surfaces are flat plates, as in Casimir's original setup, the force is attractive. The plates are pushed together, but when the geometry changes, the force can change sign. For a perfectly conducting hollow sphere, the Casimir force is actually repulsive. The sphere is pushed outward by the vacuum fluctuations inside it. This was predicted by Timothy Boyer at the City University of New York in 1968. It caused significant controversy because physicists expected the force to always be attractive. The fact that it can be repulsive depending only on the shape of the boundary reveals how deeply the geometry of a region shapes the quantum vacuum inside it. Different shapes allow different sets of virtual photon wavelengths to exist. The imbalance between inside and outside can push in either direction. The Casimir effect is not just a curiosity. Engineers building microelectromechanical systems, tiny machines with moving parts measured in millionths of a meter, have to account for it. At that scale, the Casimir force becomes significant enough to cause flat surfaces to stick together unexpectedly. Researchers designing nanotechnology must either engineer around it, or, in some proposed applications, harness it. The vacuum has entered the engineering problem. There is another place where quantum fluctuations producing real particles becomes impossible to ignore, and it involves one of the most extreme environments in the universe, the event horizon of a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. For most of the 20th century, physicists assumed that black holes were permanent. They could only grow by absorbing matter and energy. They could never shrink. They could never disappear. Then, in 1974, Stephen Hawking published a calculation that changed everything. Hawking was working at Cambridge University, combining general relativity, Einstein's theory of gravity, with quantum field theory. The result, which surprised even him, was that black holes should emit radiation. They should slowly lose mass. They should, over unimaginable timescales, evaporate completely. The mechanism is quantum fluctuations near the event horizon. Here's the picture. Virtual particle pairs are constantly forming in the space near the event horizon of a black hole, just as they form everywhere in the vacuum. Normally, both particles in a pair annihilate and return their energy to the vacuum. But right at the edge of the event horizon, something different can happen. One particle of the pair can fall across the horizon into the black hole. Once it crosses, it cannot come back. Its partner, left outside the horizon with no partner to annihilate with, becomes a real particle. It carries real energy. It escapes into space. This outgoing radiation is called Hawking radiation. The energy has to come from somewhere. It comes from the black hole itself. The infalling partner carries negative energy relative to the outside observer. This is a consequence of the curved geometry near the horizon, and that negative energy reduces the mass of the black hole, so the black hole slowly radiates its mass away as Hawking radiation. For a stellar mass black hole with a mass 10 times that of the Sun, the Hawking temperature is approximately 10 to the negative 8 Kelvin, an unimaginably cold temperature, billions of times colder than the cosmic microwave background radiation that fills space. Such a black hole would not visibly emit Hawking radiation in any detectable way today, but smaller black holes, if they exist, would be hotter and brighter. A black hole with a mass of 1 billion kilograms, roughly the mass of a large mountain, would have a Hawking temperature of about 1.2 times 10 to the 23rd Kelvin, hot enough to emit radiation detectably. Hawking radiation has not been directly observed. Black holes in the universe are far too massive, and their Hawking temperatures are far too low for the radiation to be distinguishable from the cosmic background. But the mathematics is robust, and several laboratory analogs, systems that mimic the physics of a black hole horizon using sound waves and flowing fluids or light and photonic materials, have shown behavior consistent with Hawking's prediction. In 2019, a team at the Technion Institute in Israel led by Jeff Steinhauer published results from a sonic black hole, a flowing fluid that traps sound the way a real black hole traps light, showing a thermal emission of phonons, the sound equivalents of photons, consistent with Hawking radiation. The virtual particles had, in a controlled laboratory setting, become real. Subscribe now if you want more documented science content like this. Comment your city. Back to the story. The implications reach further than black holes. Quantum fluctuations are not just a feature of extreme environments. They are the background condition of all of space at all times. Physicists call the energy of this background the vacuum energy, or the zero-point energy of the quantum fields that fill the universe. Every quantum field, the electromagnetic field, the electron field, the quark fields, all of them, has a ground state that is not zero. Even at the lowest possible energy level, the field still fluctuates. It still produces virtual particles. The vacuum is always active. The question of how much energy this activity represents is one of the most troubling open questions in all of physics. General relativity predicts that the energy density of the vacuum should contribute to the curvature of space and the expansion of the universe through a term in Einstein's equations called the cosmological constant. When physicists try to calculate what the vacuum energy density should be from quantum field theory, they get a number. When they compare that number to what astronomical observations say the vacuum energy density actually is, inferred from the measured rate of the universe's accelerating expansion, the two numbers disagree by an enormous factor. Estimates of the discrepancy range from 40 to 120 orders of magnitude, depending on the energy scale at which the calculation is cut off. 120 orders of magnitude means the theoretical prediction and the observational measurement differ by a 1 followed by 120 zeros. This discrepancy is the largest known disagreement between theory and observation in the history of physics. Physicists call it the cosmological constant problem, and it remains unsolved. Various explanations have been proposed. Some physicists argue that there must be an as-yet unknown mechanism that cancels almost all of the vacuum energy, leaving only the tiny residual that observations detect. This cancellation would have to be precise to 120 decimal places, a fine-tuning so extreme that many physicists find it physically implausible without some deeper reason. Others invoke the anthropic principle, arguing that universes with different vacuum energies exist, and that only in universes where the vacuum energy is small enough can galaxies, stars, and observers form. So naturally, we find ourselves in such a universe. Neither explanation is fully satisfying. The cosmological constant problem is one of the deepest unresolved tensions in all of physics. But the observational fact at its center is secure. The vacuum carries energy, and that energy is shaping the fate of the universe. What we do know is that the universe is expanding, and that expansion is accelerating. The force driving this acceleration is attributed to something called dark energy, which behaves like a property of empty space, like a vacuum energy. The observations come from studies of type 1a supernovae, which are stellar explosions that always release approximately the same total energy and can therefore be used as distance markers across the cosmos. In 1998, two teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, independently discovered that distant supernovae were fainter than they should be if the universe's expansion were slowing down, or even constant. The universe was accelerating. Something was pushing space apart. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for this discovery. The something that is pushing space apart is, at least observationally, consistent with a non-zero vacuum energy. The vacuum does not just fluctuate. It drives the largest structure in the observable cosmos. There is one more place where quantum fluctuations, creating particles out of nothing, becomes almost impossibly important, and it sits at the very beginning of time. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. All of space was compressed into a volume smaller than a proton. At that scale and temperature, quantum effects dominated everything. The distribution of matter in the early universe, the seeds from which galaxies, stars, and everything in them would eventually grow, was shaped by quantum fluctuations. The prevailing theory of what happened in the earliest moments is called cosmic inflation, first proposed by physicist Alan Guth at Stanford in 1980. The idea is that the universe underwent an extraordinary period of exponential expansion, doubling in size roughly every 10 to the negative 37 seconds, for a period lasting from approximately 10 to the negative 36 seconds after the Big Bang to around 10 to the negative 32 seconds. During this expansion, quantum fluctuations in the energy field driving inflation were stretched from subatomic scales to cosmic scales. Regions where the fluctuation produced slightly more energy became regions where slightly more matter eventually gathered. Regions with slightly less energy became voids. These tiny quantum variations, stretched across the sky, became the seeds of the large-scale structure of the universe. The evidence for this comes from the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old enough for atoms to form for the first time, releasing photons that have been traveling ever since. Satellites including the Cosmic Background Explorer, launched in 1989, the Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched in 2009 by the European Space Agency, have mapped the temperature variations in this background radiation with extraordinary precision. The pattern of these variations matches the predictions of inflation driven by quantum fluctuations to a remarkable degree. The spectral index, A mathematical description of how the size of temperature fluctuations varies with scale, measured by Planck in 2018, is 0.965, plus or minus 0.004. Inflationary models predict a value slightly less than 1. The agreement is tight. The temperature variations themselves are tiny. The cosmic microwave background has an average temperature of 2.725 Kelvin. The fluctuations, the hot spots and cold spots that encode the seeds of all future structure, deviate from this average by only about 1 part in 100,000. That is a temperature difference of roughly 30 microkelvin. Yet from that whisper of quantum variation, stretched across the sky by inflation, the entire visible universe grew. The filaments of galaxy clusters that span hundreds of millions of light years. The great voids between them, hundreds of millions of light years across, almost empty. The Milky Way itself, with its 400 billion stars, all of it seeded by fluctuations that originated at subatomic scales in the first trillionth of a second of time. What this means is that every galaxy you can see in the night sky, every star in every galaxy, every planet around every star, and every atom in every planet, traces its origin to a quantum fluctuation, a momentary subatomic imbalance in the energy of a field that existed before the universe, as we know it, had a single second of age. The structures you see when you look at the Hubble Deep Field image, which shows thousands of galaxies each containing hundreds of billions of stars, are the grown children of quantum noise. The particle physics community has its own way of making quantum fluctuations tangible, and it involves the largest machine ever built. The Large Hadron Collider at CERN, the European Organization for Nuclear Research, is a particle accelerator buried in a circular tunnel 27 kilometers in circumference, straddling the border between France and Switzerland near Geneva. It accelerates protons to energies of up to 13.6 tera electron volts, the highest energies ever achieved in a laboratory, and smashes them together. Among the things created in these collisions are particles that exist for extraordinarily short times before decaying. The Higgs boson, discovered at CERN in 2012 by the ATLAS and CMS experiments, has a mean lifetime of approximately 1.6 times 10 to the negative 22nd seconds. In that time, it travels a distance so small it is not meaningful to express it in centimeters. It exists, it decays, it is measured only by the particles left behind. The Higgs boson matters here because the field it represents, the Higgs field, is one of the quantum fields that fills all of space. Like every quantum field, it has a vacuum state. Unlike the electromagnetic field, whose vacuum state has zero average value, the Higgs field has a non-zero vacuum expectation value. This means the field is, on average, not at zero everywhere in space. It has a value, approximately 246 giga-electron volts in the units particle physicists use. This non-zero vacuum value is what gives particles their mass. The electron, the quark, the W and Z bosons that carry the weak nuclear force, they all acquire their masses by interacting with the non-zero vacuum state of the Higgs field. The vacuum is not just a stage where particles perform. The vacuum is an active participant that gives matter its properties. Think of it this way. Imagine trying to walk through a still room versus trying to walk through a room filled with people. In the empty room, you move freely. In the crowded room, you bump into people. You slow down. You feel resistance. The Higgs field is the crowd. Particles that interact strongly with it slow down more. They have more mass. Particles that barely interact with it, like photons, pass through freely. They are massless and travel at the speed of light. The vacuum is not a neutral backdrop. It is a medium with properties. Those properties are why matter has the qualities it does. Turn off the Higgs field and every particle that currently has mass becomes massless and travels at the speed of light. Atoms cannot form. Chemistry cannot exist. You cannot exist. The non-zero vacuum state of one quantum field is what makes physical structure possible. This is the picture that has emerged from a century of quantum physics. Space is not empty. It is filled with quantum fields, each at its lowest possible energy state. But that lowest state is not zero. Each field fluctuates constantly, producing virtual particles, exerting forces, contributing energy, shaping the geometry of space-time. When conditions are extreme enough, near a black hole horizon, in the first moments of the universe, or in a sufficiently powerful collision, virtual particles become real particles. The line between nothing and something is not a wall. It is a threshold that the universe crosses constantly, everywhere, at every scale. The energy that drives these fluctuations is not borrowed from an external source. It is intrinsic to the structure of quantum fields. Heisenberg's uncertainty principle does not say that particles sneak past the laws of physics when no one is looking. It says that the laws of physics, at the deepest level, do not permit perfect stillness. Absolute zero energy would require absolute certainty about both position and momentum simultaneously, and that is exactly what quantum mechanics forbids. The fluctuations are not a side effect of physics. They are physics. One practical consequence of this is the Lamb shift. first measured in 1947 by Willis Lamb and Robert Rutherford at Columbia University. They used microwave spectroscopy to measure the energy levels of hydrogen with extraordinary precision. According to the Dirac equation, the relativistic quantum mechanical equation for the electron developed by Paul Dirac in 1928, two particular energy levels of hydrogen, called the 2s1/2 state and the 2p1/2 state, should have exactly the same energy. Lamb and Rutherford found that they did not. The 2s1/2 level was shifted upward in energy by about 1.06 gigahertz compared to the 2p1/2 level. This tiny difference, the Lamb shift, could only be explained by the interaction of the hydrogen atom's electron with virtual photons in the vacuum. The electron is not alone in the atom. It is constantly interacting with the seething cloud of virtual particles around it. These interactions shift its energy levels slightly but measurably. Lamb received the Nobel Prize in Physics in 1955. The vacuum had left a fingerprint in the spectrum of the simplest atom. The Lamb shift is not a small correction in physics. It has real consequences. Modern atomic clocks, among the most precise measuring instruments ever built, depend on understanding atomic energy levels to extraordinary precision. The clocks used in the Global Positioning System satellites need to account for quantum electrodynamic corrections, including contributions from virtual particle effects, to achieve the precision required for navigation. Every time a GPS device calculates a position on Earth to within a few meters, it is benefiting from calculations that include virtual particles. The vacuum fluctuations that Torricelli's 17th century tube could not have revealed are embedded in the technology that helps people find their way through cities today. The story does not end in the past. In laboratories today, physicists study a phenomenon called the dynamical Casimir Effect, first confirmed experimentally in 2011 by a team at Chalmers University of Technology in Sweden, led by Per Delsing. In the static Casimir Effect, the plates are stationary and the force is steady. In the dynamical version, a mirror or boundary is moved at a speed close to the speed of light, or in practice, changed electrically in a way that mimics this motion. When a boundary moves fast enough through the vacuum, the virtual photons it interacts with can be promoted to real photons. The mirror literally shakes photons out of nothing. The Chalmers team used a superconducting circuit whose effective length could be changed at microwave frequencies by changing the magnetic flux through the circuit. Moving the effective mirror at approximately 5% of the speed of light, they detected microwave photons appearing in pairs with correlations consistent with the dynamical Casimir effect. Empty space, shaken hard enough, releases light. This is where the science stands. Every quantum field that exists has a ground state energy that is not zero. Virtual particles appear and annihilate in that ground state constantly. Real particles can be produced from those fluctuations when conditions are right, near a black hole in the early universe, in a dynamically changing electromagnetic boundary, or in any collision energetic enough to cross the threshold. The vacuum energy is real enough to drive the accelerating expansion of the universe. The fluctuations are real enough to leave a measurable shift in the spectrum of hydrogen. The virtual photons are real enough to push two metal plates together with a calculable measured force. And the quantum noise of the earliest moments is real enough to have seeded every structure in the observable universe. None of this was obvious. None of it followed easily from prior intuitions about what space should be. It took Heisenberg's principle in 1927, Dirac's equation in 1928, the invention of quantum field theory across the 1930s and 1940s, Casimir's prediction in 1948, the Lamb shift measurement in 1947, the development of quantum electrodynamics in the late 1940s, and decades of increasingly precise experimental work to arrive at the picture we have today. Each step required letting go of the assumption that the vacuum was simple. Each step revealed more complexity, more activity, more structure in what had looked like nothing. There's no nothing. There never was. The word vacuum in physics does not mean empty. It means the lowest energy state a field can occupy. And that state is always active, always fluctuating, always producing. The universe is not built from solid matter sitting in empty space. It is built from interacting fields that cannot stop moving, cannot stop fluctuating, cannot stop creating. The void is the most creative environment in nature. In 1999, physicists at the Brookhaven National Laboratory on Long Island, New York, made a measurement of the electron's magnetic moment so precise that it required accounting for more than 800 individual Feynman diagrams, 800 separate virtual particle processes, to match the theory with the observation. Each diagram represents a different sequence of virtual particles being created and annihilated in the electron's immediate environment. The calculation took years. The agreement with experiment reached 12 significant figures. Every one of those 800 processes involved particles appearing from nothing and returning to nothing. And the only way to understand the electron sitting in front of you, the electron in the atom of the screen you're watching this on, is to include every single one of them. In 2006, a team at the National Institute of Standards and Technology in the United States published a measurement of the electron magnetic moment reaching a precision of 7.6 parts per trillion. The theoretical prediction, using quantum electrodynamics, matched it. Not approximately, not close, matched it within the experimental error. The vacuum, with all its constant churning invisible particle production, is not a disturbance in the calculation. It is the calculation. A boundary marker found exactly where the warning said it stood. The math has never been wrong.